Okay, this video deals with the problem illustrated in the upper left-hand corner here of the whiteboard. We've got a tangent line that is drawn to the hyperbola given by the equation xy equals c, where c is some constant, positive or negative. And the tangent line is drawn at point P. And we're supposed to show two separate things. Part 1, show that the midpoint of the line segment cut from this tangent line by the coordinate axis is P. And Part 2, show that the triangle formed by the tangent line and the coordinate axes always has the same area, no matter where P is located on the hyperbola. Okay, out to the right here, I've written the original equation xy equals c. Since we're dealing with tangent lines, there's a good chance we're going to have to find y prime and use that as a formula for slopes of tangent lines to the original graph. So I solve for y as c x to the minus 1, and then found y prime as minus c x to the minus 2. And what we're going to do is let P be some point that is on that hyperbola. And we'll let the x-coordinate be represented by the letter A. And if the x-coordinate is A, if you picture putting A in for x right here, for y equals cx to the minus 1, you can see that the y value for each A is going to be c over A. Okay, and also, since I'm going to probably have to write the equation of the tangent line, I found the slope of that tangent line at this point by plugging a into the first derivative. So if I put a in for x, I'll get minus c over a squared. Now we're going to go from there and prove part A and B, but first I want to take us to the Desmos graphing calculator to show you exactly what's going on over here. So here I've graphed the function or the relationship xy equals c, and I've got c as a slider here, so you can see what happens to the hyperbola as c changes in value. C gets bigger, that parabola kind of gets, or hyperbola I should say, gets further and further from the coordinate axes. Okay, so I'll leave that set at, let's say, 30 for right now. If A, C over A is the arbitrary point that lies on the parabola, there it is. And I've got a slider for A, so you can see that the point A can slide along the hyperbola also. And it can even go over to this side. I don't have the end points set so you can go too much further. But now the question is, how do I find the tangent line to the hyperbola at this point, at this arbitrary point? And we'll go back to the whiteboard in a second to calculate that, but I'm just going to show it to you right here. There is the tangent line, okay, and as A changes, the tangent line changes. And what we're supposed to be doing in part A is showing that this point of tangency is also the midpoint of the segment where the tangent line, created by the points where the tangent line hits the coordinate axes. So if I label this point here as 15, 0, and this is 0, 8, if I use the midpoint formula to find the midpoint of those segments, add the x-coordinate of the midpoint is the average of the x's. So 15 plus 0 divided by 2 is indeed 7.5. And 8 plus 0 divided by 2 is indeed 4. So that seems to work. If I come down here and actually highlight the midpoint and hide the point of tangency, you can see that the midpoint and the point of tangency are indeed the same point. So that's what we want to prove in part A. And in part B, we want to prove that this triangle always has the same area, no matter where the point of tangency is. Now notice that A has a value of 60 here. That's the area of the gray triangle. If I slide A around, that area stays constant, 60. Okay? And you might notice a relationship between the value of C and the area. C is 30, C is 60. What if I decrease C to 20? Well, the area becomes 40. What if I increase C to 50? Well, the area becomes 100. So not only does the area remain constant, we can actually get a formula for what the area actually will be depending on the value of C. It looks like the area of the triangle is always 2 times whatever C is. Okay? So let's go back to the whiteboard and see how we can kind of show that. So first of all, let's identify what the equation of the tangent line is. We have its slope. We have a point that it passes through. So if we use the point slope formula, we can get the equation of the tangent line. There it is. Y minus y sub 1, that's y sub 1 right there, equals the slope minus c over a squared times the quantity x minus x sub 1, point slope formula. Now you can simplify that so it's easier to work with by distributing this minus c over a squared times each term inside the parentheses, then adding c over a to both sides to isolate y, and you get minus c over a squared times x plus 2c over a. Okay, now what good does that do us? Well, what we want to do is find out, well, here's a graph with specific points on it. P is the point of tangency, and we're going to let Q and R represent the points where the tangent line hits the axes, the x-axis and the y-axis. So how can I find the coordinates of that point? Well, you can think of making up a little table if you want. When x is 0, picture plugging 0 into the equation of the tangent line to get the corresponding y value. So if x is 0 for this equation right here, let me go with this color. If I put 0 in for x there, the first term disappears and I get 2c over a. Okay. Now, to get the coordinates of point R, I want to know when y is 0, what is the value of x? So you have to picture putting 0 in here for y, solving for x. That'll become, well, let's see, I'll get cx over a squared, transposing that term to the left side where I had a 0, equals 2c over a Now I want to solve for x, so I'll multiply both sides by the reciprocal of the coefficient of x. So that'll be x equals 2c over a times the reciprocal of this coefficient, which would be a squared over c. So it looks like the c's cancel out. It looks like one of the a's cancels out, so it looks like it simplifies to 2a. Okay, so there are the coordinates of Q and R. Now, how do I find the midpoint of the segment segment that has those endpoints? Well, I just use the midpoint formula. So I add the x's. 0 plus 2a is 2a, and then take half of that. In other words, it's the average of the x's. Well, that's just a. Then I'll add the y's and take half of that. That'll give me c over a. That's the midpoint of QR. But that's also the point of tangency. So we just showed that the point of tangency and the midpoint of the segment created when the tangent line hits the coordinate axes are indeed always the same. Okay, and by the way, back here on Desmos, I did not get the triangle shading and all that to work in the other quadrant, or when A moves to the other quadrant. Okay, but you could do that if you wanted to get serious about it. But now we're going to part B. Show that the triangle formed by the tangent line and the coordinate axes always has the same area no matter where P is. Well, what's the area of this triangle, this right triangle? This could be considered the height. This could be considered the base. And the area of a triangle is 1/2 the base times the height. So A equals 1/2 what's the height here of this right triangle? Well, it's the y coordinate of Q, which is 2c over a. And what's the length of this triangle? Well, it's the x coordinate of R. The x coordinate of R is 2a. So when I start canceling out, one of the 2's cancels out, and the a factors cancel out, and I'm left with 2c, which matches what we saw in the graphing calculator, that the area of that little triangle is always twice whatever the value of c is, and c was this constant that determined where the hyperbola was located. Okay, so that proves, or shows at least, part A and part B for this problem. And that's how you go about it when you're doing these problems that deal with the function and tangent lines. You always want to get y prime, so you have a formula for slopes of tangent lines, and you usually want to think about the point of tangency. Sometimes it'll be a general point, sometimes it'll be a specific point, but that should give you the idea.